All right. So, in today's like little practice lab thing. Normally we would totally do this. And remember I told you that we'd always do this stuff in class. Like if we learn about something, we really physically do it. Yes, we really do this in class. So I'll explain this in a minute. An electric motor has a 10-volt power supply and is pulling 120 amps of current. Motors always pull current. You can't push current to a motor. In other words, you can't say, "Hey motor, I want you to take 10 amps of current instead of 2." uh, the motor will ask for the current and get the current. So there's no way to like push um, current to a motor. It is what it is. Whatever it wants, it gets. You can choke it. In other words, it's asking for 10 amps and only give it 2 amps. You can do that. It's not good for the motor, but in the end, you can't force it to take more than it wants. There's really no way to do that, and if you did, you'd pretty much, if there was a way, you'd probably be ruining the motor. Um, so in class, this is what we would do. We would actually have, let me get a pen here. We would actually have like a motor, and you would build a frame and all this really cool stuff, and you would get the little wires right here. And one would be negative and one would be positive, and you would hook the 10 volt power supply to it. And then right here you would put some gears and some winch and stuff like that. You would have gears and string and stuff, and then you would actually end up winding the string up, and it would dangle, and you would hang this whole thing off a table. So this would be a table, and you would have some sort of weight on the floor. So this would be the floor, and this would be your weight. And in this case, the weight is 1.5 kilograms, by the way. And you would be lifting it, like say to the bottom of the table or something. You'd be lifting it a certain distance. In this problem, the distance is 0.60 meters. Okay, so that's that many meters. And of course, the more powerful. If you guys think about this, this is not like a brain buster here. The more powerful this motor is, and the more power we send to it, more electricity we send to it, the faster it should be able to lift that weight, right? There should be do it in less time, right? So, if you remember back from Friday, this was 3 days ago or 4 days ago. The power, electrical power, is just how much current are you sending to the motor times the voltage that you're sending to the motor. And then power mechanical, that's so when we send this electricity to the motor, what is it doing? It's doing mechanical work here. So it's using energy right here in the form of mechanical energy, and it's simply mass of the object times gravity times the height you lift it, and it's divided by the time it takes to lift it. So if we want to know efficiency of a motor, I need to know uh, how much. Remember, the power you send to it, this one right here, will always be more. Okay, so that one's going on the bottom, and this one right here is the power that we're going to get out. So technically, if you want me to say it like that, this is the power out of the motor, and this is the power going into the motor, technically, right? So this is the electrical power going into the motor, and this is the power that the motor is doing. It's what is it doing with all the energy? It's spending the energy. It is. Most of the energy that's going in, or a lot of the energy going in, is getting spent in the form of doing work, like doing this power. So then we divide it by, we take mechanical power and divide it by electrical power, and then of course to make it an efficiency, a percent, we're going to times it by 100. Okay. So that's the new equation today. These two right here, these are the same equations as last week. So let's go ahead and do the math. Let's do power electrical, and the electrical power is hold on. Let's see here. All right. I think I might not have my mic working, but I might have to re-record this later. Power, electrical power, is a current, which was, what was the current of this thing? Right here. There it is. 1.2 amps. So 1.2 amps. And then times the voltage, which right here is 10 volts. And let's multiply those together, and we get 12 watts of power. Okay? And then power mechanical is equal to the mass of the object we're lifting. What are we lifting? We're lifting a 1.5 kilogram object. And times G, which is 9.8 on Earth. And this problem is on Earth. I didn't say it was on some other planet. And then times the height, right here, H. And how high is this thing lifting? 0.6 meters, right? So it's lifting 0.6 meters, 0.6, divided by the time, which is 22 seconds right here. And so if we bring out a calculator, bring out a calculator. Let me just double check something here. I just want to make sure nobody's has questions. All right. I was just checking our chat window. All right. So let's bring out the calculator here. Go to the search here, type in calculator. And let's do these. Let's multiply all the top together first. So we're going to do 1.5 times 9.8, and then times 0.6, and that's the top. But then we got to divide it by the 22. So divided by the 22 seconds, and it's 0.4 watts. So where's my pen here? So it's 0.40. Now this is going to be, I'm going to give you a heads up right now, this is going to be a very, very, very low efficiency, a terrible efficiency. Why? And if you want to look right here, I already know the efficiency is going to be very low. I'm sending 12 watts of electrical power in, but I'm only getting out not even 1 watt of power out. So the efficiency is going to be low. And remember, efficiency is equal to mechanical power right here, 0.40 watts, divided by the electrical power, and then you can times it by 100. And if we do the calculator on that one, we can clear this out, and we get 0.4 divided by 12, and then times it by 100, and I get 3.33 percent efficiency. That's really low. But what that means is that 3.3% of all the energy you're going to the motor is actually doing stuff with it. The rest of it goes to heat. Okay? So in other words, if you're wondering, where's all the other energy? You know, I'm sending all this electricity to the motor, and it's doing stuff with it, but where's the rest of it going? It's going to heat, and that's why electric motors will get hot and stuff like that. This is a really bad efficiency. Electric motors are usually pretty good, and they can usually produce like maybe like 80% efficiency, 90% efficiency. You know, I think the best electric motors are like 92% efficient. But depending on what you made and when you made this thing, a lot of it's going to heat, some of it's going to vibrations. If you feel the machine vibrating a lot, that's a lot of that energy is vibrating the machine, but that doesn't do anything, but it does spend energy. To vibrate something requires energy. So the machine's vibrating a lot. And it could also go to just noise. If it's really noisy, well, it takes energy to make noise. So this motor is wasting energy making noise, it's making heat, it's making vibrations, but it's also doing what you wanted, which is this. So in this case, we would say that this motor is 3.3% efficient, really, really low. That means 97% or almost 97% of the energy is wasted. And that's how you would solve it. Pretty much you look at the power going in and the power going out, and you pull the data that you need out of the problem, and then you do the two math problems, and then you do this efficiency equation right here, and you divide them. So you take your two answers and you divide them in the right way, and you'll end up getting a fraction, and then times it by 100, or like a decimal point, times it by 100 to turn it into a percent, and you're done. Any questions? If you guys have questions.